Okay, so my name is Ida Lu, and today I'm going to talk about how to use a quantum electrodynamical density functional theory to do some simulation for like materials inside the optical cavity. And basically, before we dive into, then we have to figure out where we are. So we already know like from the day one and from Professor Rubio and Professor Kono, we already like learned the basic idea about the whole field looks like from the theoretical side and also like from the experimental side. And after that, also on day one and day two, then basically Luki and Markus, they go through like the basic fundamental like mathematical or fundamental physics model, like a quantum electrodynamical, like a polytheist Hamiltonian. And basically there you see like how we construct the Hamiltonian and some technical issues about the Hamiltonian itself. And after we dealing with like a Hamiltonian, and basically on second day in the afternoon, Mark talks about how to like dealing with the cavity photon modes. So you guys already know how to like using like once you give given your cavity, then basically you can construct how the photon modes response inside this cavity geometry. And after that, yesterday, basically like Simone and Professor Marso, they mentioned like they start to combine the materials and the photon, like this cavity geometry to figure out what is the physical phenomena you can see in this kind of like cavity material hybrid stuff. Okay, so today we are going to, after this kind of like introduction, today and tomorrow, basically we are going to use this kind of like cavity things to, to engineer, like put solid state material inside and also like molecules and atoms inside this cavity geometry. And if usually we kind of like split this field into two subfields. One is like if you use a solid state material inside a cavity, basically we call it cavity materials engineering. And if you use like molecules and atoms inside this cavity and do something like chemical reactions, and basically people call it protononic chemistry. And this is also a very big field now. Okay, so now today what we are going to do is basically we are going to focus on the material inside this optical cavity itself. So basically the photon mode constructed by this optical cavity is already done, like introduced by Mark the day before. So today we are going to focus on this material itself, and particularly we want to use the ab initio method to deal with this solid state because you have a bunch of materials in the world. So in order to capture that, then basically the DFT is one way to do this realistic materials calculation. Okay, so before we dive in, then basically I want to do a quick survey. So how many of you seeing yourself as a physicist? Okay, and how many of you seeing yourself as a chemist? Okay, engineer? Okay, mathematician? Okay, oh, just one, okay. Right, and also I'm curious about like how many of you are first year and the second year graduate student? Okay, just very few. Okay, and then how many are postdoc or almost like going to graduate soon? Okay, good, thanks. So today we are going actually, now I need you guys to pair with each other like two. So because today we are going to dive into an adventure. And okay, so it's like I'm your tour guide. So I basically, yeah. So basically here I'm not trying to like give you some like knowledge, but I mean like I will guide you to construct the functional by yourself at the end. So okay, so there are many things that we have to go through. And basically, I'm going to provide the food of thoughts and also the tools to guide you through. Okay, so now please take like 2 minutes to pair each other. If you don't know each other, please introduce yourself. I mean, like, yeah, just find another guy, your fellow, and because your fellow probably will help you during this journey. Yeah. Okay. So if you already find like your fellow, please raise your hand.
Okay. It would be cheating to work with the TA.
And then if you haven't found, because during this lecture, I will ask you guys just randomly pick up some of you, and I will ask you questions. Okay, so you have to make sure that you have a fellow with you to discuss. Okay, so it seems like everyone is already ready. If you haven't found your fellow, please raise your hand.
I don't think for some reason she chose to go. I don't count those. You have Markus. Well, not a better one. Markus, next to you. He's a partner. Who's unpaired? Can you guys raise your hand? I mean, I guess, yeah.
So you have like a. Okay, good. Lucas, you have anyone? Okay, Kevin, you have. Okay, good. Good. You guys. Okay, 3.
But maybe Ethan, there is one here.
Okay. Can you go? Please go. Yeah, please go. Or do you want to? Some of you want to move here? Okay. Yes. Sorry.
I guess so.
So you okay? Good. You have someone. Okay, good. Lucia, you have someone. Okay. Okay. Do you want to like go?
A couple of cluster people are going to be.
Oh, you have so much. And do you have like have you paired with someone yet? Have you ever like paired with someone already? Okay, maybe you want to. I mean, like maybe.
This morning,
you like?
People are going to use that because we're calling our functions.
Yeah, because
I'm not so agile anymore. I feel more the mountain.
So you guys have a pair, right?
Yeah.
Okay. And then the last one. Okay, good. Okay, so today, now we are going to go to the jungle. Yeah. Okay, so today, like, I will give you the map. So basically, the first thing is that we are going to, because now we are dealing with the material inside the cavity. So it's a big master. So the first thing is that we are going to partition the electron, nuclear, and the photon system into a subsystem. And after that, once you partition into a subsystem, then basically the way we are dealing with a subsystem is a so-called density functional theory, or DFT and the QEDFT. And basically, Markus Sensei will guide you through the mathematical construction about how to do this mapping. And after that, we are going to use, because in DFT, there's an issue about like, not issue, but I mean like, because the challenging thing is like to find a functional. So we are going to use a method called local force balance equation to find the functional, like the exchange correlation potential. And after that, but this approach is general for like electron interaction and electron-photon interaction. And after that, we are going to take this method and apply to the electron-photon exchange interaction, correlation interaction. And after that, at the end of this lecture, so basically you are going to construct your first QEDFT code by yourself. So we are going to have like a Jupyter notebook. Okay, so now we are going to enter into the first step. And before we go into the jungle, basically you just keep about like our learning objectives. So the first thing is that we are going to partition from, I'm going to do this for you, just for the electron and nucleus. And probably most of you are already from the quantum chemistry background. Probably you already know how to partition electron and nuclei. And basically, I'm going to do the easiest part for you. And then after that, I'm going to ask you guys to figure out how to partition electron, nuclei, and the photon system into a subsystem by yourself. And that approach is basically a so-called generalized Born-Huang expansion. And after that, and then basically you also need to understand how to expand QED, FT, or DFT to each other. Okay. And after that, you also need to know what is the practical challenge there. Okay, so the first thing is that I'm going to just give you just a review. So here we're just looking into the basic matter Hamiltonian, which has an electron and nuclei. And here this is a Hamiltonian. So in this Hamiltonian, we have the kinetic energy from the electron system and electron Coulomb repulsion. And basically this is a longitudinal interaction between a electron and a photon. And here we have a nuclei kinetic energy, and this is a Coulomb impulsion from among nuclei. And this one is the electron nuclei attracted Coulomb interaction. So basically I written the exactly form here. So you can see this is an operator. And here, one thing I need to point out, you already see this is a Coulomb kernel. And this Coulomb kernel, as you already know, this Coulomb kernel is from this Poisson solver. And basically, if you use a different boundary condition, you are going to get different kernel. So let's say, if you have a cavity geometry, if you using different boundary condition to quantize your photon mode, basically you are going to get different Coulomb kernel. So usually what we do is we have to use a box, and basically we put the potential go to vanish, go to immunity. So that's why we have this Coulomb kernel here. Okay, just one thing you have to pay attention to. So the goal is that in quantum chemistry, what we do is we want to find this solve this eigenvalue problem. Okay, so you have to know one thing before there's an exercise for you very quick, just one slide after. So basically you have to notice that now I written the electronic coordinates and the nuclear coordinates as this kind of like a form. So it means the underline basically it means 1 electron to NE electron. And also similarly for the nuclei. Okay, so this is some hints for you, the question I'm going to ask you later. Okay, so now once we have this big master, then basically the first thing is that we want to partition this electron and the nuclei system into a subsystem. So the way we do is we collect all the quantity related to the electrons into a Hamiltonian. So here we have a kinetic energy for electron, Coulomb interaction, and electron nuclei interaction, and also nuclear interaction. But here you notice that I put a curly parenthesis around this R. So this R means it becomes parameters. It's not like a quantum operator anymore. So for this fixed nuclear position, basically for each fixed nuclear position, I have a corresponding electronic Hamiltonian. And for this electronic Hamiltonian, we can solve the eigenvalue problem. And so this wave function is called conditional electronic wave function. And once you got this eigenfunction, so basically you form a basis set for this fixed nuclei position. So we can use this basis set to do this expansion for the original 4-wave function. Okay, then you plug this 4-wave function back to the original Hamiltonian the original Hamiltonian basically has a nuclei like a kinetic energy operator. Okay, and so once you plug in, then basically you can do the math, easy math to get this. Do you know how to get this? This formula, like a equation for the nuclei wave function. If you don't know, we have a bunch of resources in the audience who is doing quantum chemistry. So maybe your fellow know how to do this. Okay, so once you get this nuclei, like a equation for the nuclei wave function, and then what we do is like usually what we do is like we use a adiabatic approximation or so-called Born-Oppenheimer approximation. And the idea here is like we get rid of the off-diagonal term because during in this off-diagonal term, they usually include a nuclear mass, and nuclear mass is quite heavy. So that's why we get rid of the off-diagonal term. And what we left as is like the equation at the bottom. So the equation at the bottom basically means your nuclei now sitting on the energy potential surface. Okay, so okay, now this is everything I provide you to go through the first side. So the question now for you is like, if I start from this Pauli field Hamiltonian, okay, before we go into the question, basically the first, something I want to ask you is like, what is this mass means? It's a physical mass or bare mass? If no one, I will just randomly pick up one to answer this question. So for this Pauli field Hamiltonian, what is the mass here in the orange color? It's a physical mass or bare mass? Okay.
It's the bare mass.
Okay. Anyone else? Okay, so actually, like it depends which the photon mode you deal with here. So for example, I mean like the bare mass actually is right. In the Pauli field Hamiltonian, usually it's like we start from the bare mass, and the photon field here we're dealing with is like a continuous photon mode. And so basically, if you remove the free electron, like a free continuous photon mode, then basically it will become a physical mass. And here, what you left as is like some effective photon modes, like what Markus showed in his lectures. Okay, and another thing here is that I want to point out is, as I said before, this Coulomb kernel, basically, when you see this form, it's already have some implicit boundary condition already applied. Okay, so you have to make sure that your boundary condition, if you change the boundary condition, basically you are going to change this form. Okay, so now this is a question for you. So now now you have you pair with each other, and the question I want to ask you is like start from this Pauli field Hamiltonian, and then if within the long wavelength approximation, okay, this Hamiltonian, how are you going to partition this giant monster based on the method I just introduced to you for the how to partition matter Hamiltonian? Okay, so now we start from now, and then I will give you 10 to 15 minutes. And probably during your discussion, you will start to see what's the issue there and what is the challenge there. And then at the end, I will ask you what kind of like things you found, like what issue you found, and maybe you can try to figure out how to get this kind of like formulation. Okay. Okay, so let's get started.
Is lowercase psi the like many body electronic wave function? Nuclear.
And if you have any question, you can just raise your hand. I will go there.
Okay. for every set of nuclear positions, you can solve the electronic wave function. And index is like, I think right now it's like this. So the issue being like you can't over some linear combination of the, and so it's basically like you have like the ground state or like the electronic ground state. Say like presumably at low temperature, like it would be dominated by like pi. I mean, you could like
what kind
like pi j.
question?
Like,
Oh, so the question is like
actually
start from the polyfield
it's not like
Hamiltonian.
a perfect.
How are you going to partition the Hamiltonian into like a small subsystem?
J greater than 0.
Yeah.
The only difference between doing this for the matter interaction, so like interaction. What kind of there is no channel. Yeah,
Is there anything I can help you with?
so it's not right now. I get a play, but personally,
Oh, okay. A second.
I don't know how it is. I mean, there are different.
So you can avoid crossing or something that the energy they interact. So the nuclear particles interact as well. So you need to do the full expansion to take into account this.
Okay.
Makes sense? Yeah. Thanks.
That's right.
Both.
So I guess it's
That is
Anything I can help you with?
partitioning like
Or you try to figure out what's the question. So the question is like a start.
and also
It depends on you. Yes, that's right.
in the long
Yeah,
run,
you are going to the correct
I guess
direction.
the first thing is that you can like replace all the like
Anything I can help you? I noticed that some people they start to look into the lecture notes. Yeah, and the lecture notes have some solutions already there. Yeah. Anything I can help you? You are looking at the lecture notes. Okay. Oh, okay, good. Oh, the previous time.
so it's
Yeah, point one extension.
I don't know.
Yeah, that's right.
Yeah. I mean, it's quite normal.
I guess I feel like it probably makes things more separable.
Are you another? Yeah, you are participant. Oh, okay, can yeah.
This is right. The reason for
No, dovevamo
Oh, I see. Oh, okay, okay, okay. I see, see. Okay, okay, thank you. Anything I can help? Ah, you guys are looking at the solution. Okay.
questa materia di sera. Was that the correct term?
That's fine. I also only it was a bit of pity. It was supposed to be
Anything I can help
okay, so
anything I can help you to,
have
or
this
are
is
you
the electronic wave function, just not trying
okay? Okay.
multiply by the big that it can tell me conditional onto it, so it's fine.
Yeah, that's a one. Like,
So it's just I mean, it's like got a small.
but no, I mean like not this one. I mean like yeah, totally yes, I mean totally. And there you probably are going to see there are some issues that shows up. It's not easy to partition this kind of like. Yeah, yeah.
Because you have one method, you have one just the electronic part, and three. That's three. It's. I mean, there's still German construction. But the cleaning conditions, so one step
How is the election?
Ma no, abbiamo così perché se no non
that doesn't matter.
How can we
Right now,
partition
so
into electronic?
You will show the idea of the same
Anything I can help you?
So the question was how can we partition it into electronic?
And because now you have a new core, yes, and then they will mix things messy. Yeah.
no like gradient.
I mean, like you already start to found there's some issue not easy to predict. Yeah, I mean, like this is something. Yeah, you are going the right direction.
I mean, like for instance, just like electronic parts.
Okay, so the I or whatever it is, like you have the T. And then, okay, so that is the coefficient, the expansion coefficient that you have when you use the electronic states as a given geometry as your basis. So the Born expansion is exactly what we have. So it's telling you that for every geometry, for every
Okay, we have 30 minutes. That's 30 seconds left.
you're going to use that.
So you guys need to figure out what's the issue and then where you are going. Okay.
So here's the thing.
And those are just the guys.
That is right? In the second
How much the electronic states mix for a given geometry, that's usually the total nuclear and electron.
Let's do it up.
Okay, so time is up. Then
For now,
okay, so let's come back. And then now I'm start to walk around and then I will start to ask the question. So maybe if someone not looking at me, I will go to your place. Okay. Okay, so what kind of issue have you found? Like when you try to partition this Hamiltonian, like the polyfield Hamiltonian, have you find any issues or any discoveries? Yeah. Anything, it's okay.
Especially it is high, temporarily. Yeah.
So what? So now where are you stuck now? When you do the partition.
Evaluating the Born expansion for the entire polyfield Hamiltonian.
Okay. So you don't know what kind of a form you should use for the expansion.
Yeah.
Okay, good. And then let me thanks.
Yeah.
How about you guys? Do you have any discovery?
Yeah, we have some discovery. It's not working. Yeah, so this Hamiltonian, I assume the electron mass and the ion mass are not given, so I would treat them on the same footing instead of applying the Born-Oppenheimer approximation in the beginning.
Okay.
And naively, I would think the coupling will come from the minimal coupling, the phase fixing. I will expand the P plus EA term, just expanded.
Yes.
And then the P square will belong the matter part, matter Hamiltonian. And the A square will goes to the light Hamiltonian, and then we normalize the effective mass maybe in the end. Then the light matter interaction will be P times A for both the electron and the nucleus. And it depends on our purpose. If you want to renormalize the matter Hamiltonian, maybe I will take the light matter interaction into the matter Hamiltonian and treat them by some ways.
Yeah, thank you. Very good. I mean, you go very far away. Okay, so maybe I can try to maybe. Because I noticed that some people already look into the lecture notes, and this is a smart way. Because I put the answer there. Maybe I can ask you. Do you have any discovery?
Oh yeah,
like any issues or some difficulty you have found during this exploration?
Basically, how to I think especially the term that the coupling between electron and nuclear.
Okay.
How to move this?
I see. Yeah, thank you. Maybe next one, the other side. Do you have any discovery, or insights? Anything is okay.
Which insight?
You can switch the microphone on.
Oh yeah, I already switched.
Is it on?
Yeah, it's on.
We considered the Born-Oppenheimer approximation. We also considered that perhaps we could neglect some portion of the interactions with the nucleus, like the light nucleus interactions. That's what I mean.
Okay. No problem. Yes, that's good. So let me tell you a story. Usually, like when I start to do this kind of like a theory stuff, the first thing is that I try to make several errors, and this is especially in Angel's group. We have to make several failures before like succeed in one case. Yeah. So this is quite good. I mean, like also like during research, you always like you need to try. And once you try, you will figure out which the best way. And so usually what we present is like the best way we have found. Yeah, so you don't have to worry about like if you have some insight, this is a good thing. I mean, like there's no bad insight or good insight because it's a way to lead to for you go forward. Okay, so now I'm going to show you what I would do, but this is probably is not the best way. This is just one way. So the first thing is that, as I showed you before, like for this Hamiltonian, basically I will write down like in terms compared to the matter Hamiltonian. Now you are going to get another parameter, non-parameter operator here. So basically, in addition to like the electronic Hamiltonian, so you have a kinetic energy and the electron repulsion. And we also have a nuclear Hamiltonian, which contains the kinetic energy for nuclei and also repulsion for the nuclei. And additional to this electron and the nuclei, now we have a photonic Hamiltonian. And this is the way I kind of like organize them. So I put like a diamagnetic contribution for this A square into this photon oscillator. And basically I define this HP. Okay, so after that, basically, in addition to these three pure electronic nuclear and the photonic Hamiltonian, we also have the interaction between different sectors. So we have electron nuclei and electron photon. Basically, this is a paramagnetic contribution. And also we have a paramagnetic contribution from the nuclei and the photon itself. And the issue now is like we also want to solve the bottom line, this Hamiltonian. And as you already see, it's very cumbersome to solve this. So that's why we have to do the partition. So the partition probably you already encounter is like initially we have two. One is the electronic and one is like a nuclear coordinate. But now we have three. So it depends on how you are going to partition the system. So one way is like you group nuclei and the photon into the same subsystem. And in this approximation, people call it like a partition. People call it a cavity Born-Oppenheimer partition. So the case which this one works well is like if your photon frequency is kind of like very close to the nuclei vibration frequency. And basically because they kind of like move the same speed, so we kind of like group them into the slow subsystem. And the left, so what we left is the electronic system, okay? And another way is like if your photon frequency is quite fast, then basically you can group the electronic and the photonic coordinate into the same system. So this is called electron photon subsystem. And this one is a nuclear photon subsystem. And you also have just a electronic system here. Okay, and there's one question about like some people mentioned, yeah.
Thank you. What nuclear energy scale do we mean? Do we mean like phonon excitation?
Yeah, phonon excitation. Something. So it's like around femtosecond, usually.
Okay. Thank you.
Or terahertz. Yeah, so there's one question from this side. So basically, let's say how many subsystems we should partition into. So basically, if you from this one, you can see there's two coordinates here, and actually you can keep partitioning. So if you keep partitioning, you will become the so-called explicit parallel partitioning. And okay, so this is a starting way you can do. And now, because what we have seen is like we start from the polyphase Hamiltonian in the velocity gauge. And there's another way people do is like they from the polyphase Hamiltonian in velocity gauge, they do a unitary transformation. This unitary transformation is called power pole. Okay, yeah, okay. So after this, it will become the polyphase Hamiltonian in the length gauge. And there are some papers I put here, and then they do this either this cavity Born Oppenheimer partition or so-called Platonic energy service partition. Okay, so if you are interested, you can look into the paper I list here. There's one question.
Where's the photonic wave function?
Oh, the photonic wave function. So here is hidden inside, or you in this case is hidden here. So you can also like partition that, but it depends on which subsystem you are going to look into. Okay.
But is A here just a classical field, or is it the operator?
So for this one is in this case is an operator. When I put a curly brackets, basically it's a parameter. Okay. Okay. So now in the next few slides, basically I'm going to use the so-called Platonic energy service partition. I'll choose this system because we are going to couple the electronic system to the photon system strongly. Okay, so this is what we are going to do for the QEDFT stuff. There's a question.
So the first approximation, this cavity Born Oppenheimer, is this? Can I think about it similar to like a mean field decoupling of the electronic sector and nuclear?
Yes.
And
so I mean like here the electronic system will feel like there's kind of like because it's fixed nuclei and the fixed photon coordinates. So it's kind of like living on the energy landscape created by the fixed nuclei and the photonic coordinates.
Does this in retrospect mean that I cannot expect to see polaritonic excitations in this type of approximation?
I mean like you can still see here, like if you.
But you should say there's no approximation.
Okay.
Really repartitioning, you could say. So at this point, there's no approximation. It's very important.
In order to calculate.
Approximations come at the latest.
Yeah, I would need to drop the coupling terms between the highs, right? In order to do calculations, and then it would be a proper mean field.
Yes.
And you are going to see the coupling term later in the next slide. And it seems like there's a.
So A is a parameter.
A is a parameter, but like if you were to realize this like computationally, it would be like you'd have to like A would be like a 3-vector on like a mesh. It'd be really, really like.
It's like another. If there's only matter like a nuclei and an electron, so basically in that system we have a nuclei position everywhere. So the electron will kind of like feel there's an energy potential for it. And in this case, you have another degrees of freedom for this one, because you have a degrees of freedom from the photon part.
I'm asking like the computational complexity, because you'd need like a basis for every like parameter, like every A in the parameter space, and the parameter space is like really big because it's a vector potential.
Also, it depends on how many photon mole you are considering. So if you use let's say one effective photon mole, then basically you only have a one degrees of freedom. Yeah, but I mean I agree with you. If you consider more photon moles, then the degrees of freedom will become larger. But this is also similar if you increase the number of atoms in your system to do DFT or something. Okay, so now I'm going to choose the second partition, like a polyatomic energy surface partition. So what I choose is that I collect all the electronic and the photon degrees of freedom together. So I have an electronic Hamiltonian electron nuclei, but for the nuclei, basically is a parameter. And we also have an electron photon and photon itself and the nuclei, and this is also the parameter. So basically here, if we know this Hamiltonian, we can solve the eigenvalue problem. So this eigenfunction becomes a basis set, and then we can expand the exact wave function in terms of this eigen basis set. And this one, this is a nuclear wave function. Okay, so if we plug this one back to the original Hamiltonian, you are going to get this equation for the nuclear wave function. And for the off-diagonal term, if the mass is quite heavy, so we can get rid of diagonal term. And there is a caveat. If you look into the lecture notes, there's a sum of diagonal term, which is C and D here. They will include the photonic degrees of freedom. And if you are going to see if the frequency becomes very small, then your off-diagonal will become very large. So in this case, we cannot no longer neglect the off-diagonal term. Okay.
What's the physical meaning of ABCD?
Oh, ABCD is like do you guys have the lecture notes? Maybe I should. It's already in the where is that? This one. So if you look into your repo, like a GitHub repo, and basically you are going to see the ABC term is shown here. Okay. So if you get rid of the photonic coordinates, basically we go back to the electron nuclei system. Okay, and you can see like if the mass is quite large, then basically we can get rid of diagonal term. And but for the C and D of diagonal term, then basically you are going to see there's a A field, but the A field this term will become very large when your frequency goes down. Okay. So let's go back almost there. Okay, so we assume that the mass is quite large. So we can use a so-called Born-Oppenheimer approximation. And the physical meaning of this one is like now the nuclei sitting on an potential energy surface. But this energy potential surface is constructed by electron and the photon together. So it's called polyatomic energy surface. Okay. Yeah.
So here, when we adopt this polyatomic approximation. So I guess we assume the photon frequency is way larger than the highest phonon. So that means we assume we work in a physical setting that your h bar omega, the effective mode, is way larger than the materials.
The phonon frequency.
So is that valid when we work with such
a system? Yes.
Or can we so in certain situations we may violate that assumption, right? Is that possible to violate that?
I mean, like if your photon frequency is quite close to the phonon frequency, then you will violate what we are doing here. And basically here you have to consider the off-diagonal term to get the phonon right.
So what about in experimental setup? Do they know what is effective h bar omega?
So I think it depends on the cavity setup they are using. I mean, like if they are in terahertz, probably there will be some issue there.
Okay.
Yeah.
Then you have the other partitioning.
Yeah, you have another partition. It's a cavity Born-Oppenheimer. Yeah. So there's a kind of like a trick. I mean, like it depends on which photonic cavity you are looking into. Yeah. And then you can choose which partition you should use. Okay, so let me see where. Okay, so now once we partition the whole electron nuclei photon system into two subsystems. One is a coupled electron photon system, and the other one is a nuclei system sitting on the polyatomic energy surface. But the issue here is like, even though we already partitioned, but we still don't know how to solve this polyfield Hamiltonian, only include the electronic and the photons. And there's one thing I want to mention before we jump into the DFT and QEDFT mapping, and Markus will cover this. So once you have like a nuclei sitting on this polyatomic energy surface, and basically the force here, it will obey this kind of like so-called Helfer-Maiman formula. You can try to prove this if you want. And also like for a solid state, you can do this from this minima, energy minima, you can do like a second harmonic approximation to get a phonon and the related phonon. Okay. So as I said, solving this polyfield Hamiltonian for the coupled electron photon system is still very challenging. And that's why we need a QEDFT to do this, to solve this Hamiltonian. So now I'm going to head to Markus' lecture. So now you already like you reach this summit. Okay, you already get some ideas about how to do this partition. And the next thing is that Markus is going to cover the DFT and QEDFT mapping. So I'm going to switch.
Okay, thank you so much, Ite, for preparing my part of the talk. Okay, so I will start with basic density functional theory. So we take everything that we learned now and we see, okay, if we have different subsystems in our whole physical system, we have the possibility of hopefully partition them in some sense. And in this context, ordinary DFT is only concerned with the electrons. So we already have a Born-Oppenheimer approximation if we come from usual chemistry, or somehow we already get rid of the photons, but we will see later how to include them. So now, first I will deal with the traditional DFT approach, and then extend this to QEDFT. And in this whole short section, there's little sub-learning objectives. So I hope I can tell you the basic ideas, also mathematical ideas behind density functional theory. Then we should understand how the Kohn-Sham method is used to approximately solve such systems. So the Kohn-Sham method is not the same as DFT, but it's one practical implementation, and it's the most popular one, and that is mostly applied. And you will see why it's very practical. And then in the last step, we extend this to QEDFT. So what is density functional theory? Since a long time, this is really a highly popular quantum mechanics computation method used to solve electronic structure problems, mostly in the ground states. It's used for molecules, solids, and other systems. It builds, and that is important, like mathematically, it builds on a very deep and profound connection between external quantities that are just the parameters and the Hamiltonian, like the external potential, and internal quantities used to describe the state of the system. So you replace the very complicated wave function by a very simple object, like in fluid dynamics, you could say, and that is just a charge density. And then in all variants of DFT, this is always done, follows always the same outline. There's always external parameters and internal densities in a generalized sense. This could be the current density, this could be the expectation value of the A operator that we've just seen in this reparametrization, or other quantities. And then on top of this formulation that we call DFT, the Kohn-Sham method is a practical implementation, and it replaces this complex interacting many-body system with an auxiliary system of non-interacting particles. Non-interacting particles are very easy to solve. So there we know how to solve it. We just solve one particle Schrödinger equations, and we use approximations to do that and to relate back to the interacting system. So as you see, my Hamiltonian doesn't include photons, it doesn't include nucleons. So we are already in a partitioned setting. We are only concerned with this kind of Hamiltonian. where we first have an external parameter. This is this external potential V. It's just a scalar potential here. There's the kinetic part for the electrons. There's an interaction, and I have some scaling parameter in front of the interaction. So I can switch it on and off. Lambda 0 means off, so non-interacting electrons, the easy system that I can easily solve because it's only independent one-particle Schrödinger equations, and the fully interacting one, which could be lambda equal to 1. So whenever you see a 0 on top, it means non-interacting. Whenever you see a 1 on top, it means interacting. Okay, and I add for every particle this external potential. So nothing so special here. And now the quantum mechanical ground state follows from the variational principle for the energy. This is called the Rayleigh-Ritz variational principle. So I go over the set of all possible states here. Those are all normalized states in my Hilbert space. I calculate the expectation value with respect to the full Hamiltonian that describes the full energy of my system. I choose the state or one of the states, it could be many due to degeneracy. I choose one of the states that give minimal energy, and this I call the ground state. As easy as that. And I assign a ground state energy to that. And you see, I parameterize this ground state energy first with the lambda, so the scaling parameter for the interaction. So there's a ground state energy for the non-interacting system and the ground state energy for the interacting system. They, of course, don't agree. And I also parameterize with the external potential that is just put into the Hamiltonian as a parameter. And the minimizer here, if I find one, so there's an infimum here. The infimum is different to a minimum. The good thing about an infimum, it always exists. Minimum does not always exist. What can happen? Take, for example, a free particle in space. Is there a ground state? No, right? You just have scattering states. There's no bound state in a vacuum. So only when the V allows a bound state of so and so many electrons that I put into the system, and I always keep this number fixed, then there's a minimum. So only if V is a binding potential, like we would have in case of molecules or also solids, then we would really have a ground state here. Usually we think that is the case, but just be aware that this does not have to be the case always. Still, this quantity is well defined. Okay, there's always an infimum. Why is there an infimum, and why cannot this be minus infinity? Do you have an idea from my first talk? There was one, I mentioned two important properties of the Hamiltonian that is also true for the Pauli-Fierz Hamiltonian. Hamiltonian is always a self-adjoint operator, right? And the second property was? Yes, bounded below. Bounded below means there's a lower number here. That's exactly bounded below. So you cannot decrease the energy to minus infinity. That is bounded below. And that's why we need it in order to find a ground state potentially. That's why this was an important property in the formulation of my quantum mechanical setting before. Okay, and in principle, the structure would be exactly the same, including nuclei, and it will be later the same, including photons. So this doesn't change. This is a very general construction. And many, or all, no, of course not all, but many problems in quantum chemistry and solid state physics have this universal form. So they are described, or we want to describe them with this basic Hamiltonian, and there's a universal part of the Hamiltonian. This is the first part. This doesn't change in a huge class of problems, while only this part here changes. But this is just a relatively simple parameter. So we want to somehow harvest from this universality of the problem and make our whole problem simpler. And for this, we switch from psi to the charge density that is just defined by integrating out all coordinates, all particle coordinates except of one, and we get this one particle charge density. Okay, so what is the universal density function? That is the prime object of DFT. So here's the same Hamiltonian again. And I write down exactly like before the ground state energy, nothing has changed, and I rewrite it a little bit. So I put in the Hamiltonian here, I take the universal part here, and I take the external part. And I see that if I take the expectation value with respect to psi, this can be written as the integral of v times the rho and integrated over all positions. That's a nice and easy reformulation. And now we see why the density is special, because it couples in this way to the potential. And this is mathematically, this is a dual pairing in some LP spaces or some Banach spaces. And this is extremely useful for what comes, because now we can say, okay, I don't take the variation over all wave functions. I take only the variation over all possible densities here, because then I already know what to put here, and that is the density. So I can separate out this part of the equation. And in the universal part, the part of the Hamiltonian that stays the same for my huge class of interesting problems, I still put in the wave function, but only the wave functions that map to a specific density. So I hope you can see that this line and this line is the same. So I make two steps of this variation. First, the crude step, so to say, just fixing the one particle density. Of course, there's a lot of wave functions giving the same electronic density, but this part of the Hamiltonian does not change. This is the same for all densities. So only this part changes. But now you see that this whole part depends only on the density. And of course, on the, if I switch the interactions on or off. So this is the universal density functional. It's a functional because it maps a function to a number that is called a functional. And if I know that, I'm done. I can calculate the ground state energy by making this simple variation problem over only densities, which is a very primitive quantity compared to wave functions. Of course, this is not a simple expression or anything, but I can write it down. So all the complexity of my original many particle system, when it comes to ground state energies, is compressed into this functional. Okay, that is the basic idea of density functional theory, or of all functional theories. Also those who will be invented in the future. Probably. Okay, so we replace the complicated object of a wave function with the simple object of a one particle density. It is very much in the spirit of classical hydrodynamics, I would say. So I have, if you think about the Navier-Stokes or Euler equation, I would usually say the basic quantities are density and current. And I can describe very complicated systems with this equation. There's very complicated flows, but underneath there's maybe a single particle model. But I'm not concerned with the single particle model. I only look at these continuum quantities. I have high order of nonlinearity, but simple quantities. Okay, and computationally, in some cases, this is very useful. Okay, now I tell you the Hornberg-Kohn theorem. So first, I want just to highlight that a given V, so a given external potential could, of course, allow degeneracy in the ground state, and different degenerate ground state could all lead to the same density, if it is, for example, just spin degeneracy, or they could also lead to different minimizers. So here before, if I look for the minimizer here, there could be multiple ones still due to degeneracy, just to remember that. And at the minimizer, so now I think like rho is the ground state density for a given V. I have this equation fulfilled, of course. So the statement of the Hornberg-Kohn theorem, this is from 1964, so it's already quite old. In the special continuum setting, so the usual setting of quantum chemistry, there is only a single potential up to adding a constant from a well-defined class that yields a given, or that yields a ground state density that comes from a well-defined ground state psi 0. So the interesting thing is, so this is always given as the basic theorem of DFT because it allows you to go from densities, if you have a given density that comes from a ground state, back to the potential in principle. So that's why this is always formulated at the beginning. But one has to take it with a grain of salt. So there's many settings where this strict form of Hornberg-Kohn is not true. So we discovered that in lattice settings, for example, it's not even true. So one needs to be a little bit careful. But and also for a lot of the formulation of DFT, one doesn't need it. So one never needs the Holm-Bacon theorem. Still, it's always presented at the top of DFT. I put it a little bit on a later slide. And the problem that occurs is that not every psi in my huge Hilbert space is necessarily a ground state for any potential. So that also means that not every rho is given from a V is the ground state for a given external potential V. And that is known as the V representability problem. And that is the big problem in the mathematical formulation of DFT. So in order to solve it, the wish is to find nice function spaces that we can work with, where the densities are in a space X, and the potentials are in a dual space X prime. Why dual? Because they are grouped in this integral rho V and integrated over the position. So that is a dual pairing. That's why mathematically this is a dual space. And that the densities, so of course the space, not every element of the space is a density, but if I take them normalized and bigger than 0, then this is a physical density. So I take out those elements, and each one of that should be the ground state of a given potential. So that would be the wish, and this is how people think about DFT, that this is actually the case. It's not. It's not in all current formulations of DFT. So one has to be extremely careful about the objects one works with, and not think that automatically every density has a corresponding V. But if it has, it's unique. Yeah, and in this ideal setting, so in this wish, and we are working on realizing that, there is a one-to-one mapping. So every density, under these conditions here, every density has a potential, every potential has a density. Goes both ways. Yeah.
So regarding the Holmberg-Cohen theory, which is not true in a lattice setting.
Yes.
Can you explain more about this point?
Oh, it's very simple. There's just very basic counterexamples where you can choose one density, and there's an infinite number of potentials realizing exactly this density. And it's not just adding a constant, it's really different potentials.
That means we have a discrete lattice, right?
Yes, you have a Hubbard, like think about a Hubbard system with a very few lattice sites. So I can show you examples with just 3 or 4 lattice sites where there are densities that are such, and usually this is due to or is always due to some symmetry. And you can easily find that there are infinite numbers of potentials giving you the same density. And this is just a counterexample to this. But you can show also that these are not like, if you take a random density, this will still hold. So it's not that terrible, so to say. Okay, now up to this point, there was no approximations involved also. I mean, DFT is of course always formulated as approximative method, or it's used as an approximative method, especially also as in the Kohn-Sham approach. But up to now, there was no approximations involved whatsoever. I defined this F functional here. This is the exact F functional, so to say. It really could lead you to the correct ground state density. And what we will do now in order to facilitate approximation is we introduce an auxiliary system of non-interacting particles. So here is now the lambda equal to 0. That is the Hamiltonian collapses to just kinetic part and external interactions. And traditionally, the external potential is called here with a, it's written here with a S, and nobody knows why S, I think. Maybe single particle, or maybe Slater, I don't know.
Mystery. Nobody knows.
Maybe Sham, yeah. Okay, so this is the simpler Hamiltonian, and we would know how to use this, how to solve this system, right? This is effectively, of course, this is many particles, but I would just solve it as a one-particle equation and then fill up from below. And then Aufbau principle gives me an antisymmetric wave function, and that I would take as the ground state solution. Easy as that. So now take a density that is interacting and non-interacting V representable. So we assume that the density is such that I can find a V and a Vs, such that putting the V into an interacting system, I get rho, and putting the different Vs in a non-interacting system, I get the same rho. This is always the idea behind Kohn-Sham. I have two different systems, but they are connected over the density variable. So two different systems with two different, one interacting, one non-interacting, with different external potentials, give the same internal variable, the density. And this creates this connection that I will use to derive what you will see here. And how you write it is, so this is the external potential in the interacting system. Then one usually separates off the part, the mean field part that is already known, the Hartree potential of the given density, because this is just the classical easy mean field part, and I know it already, so why not take it into account already? So this is part of the interactions clearly, right? And this should give the Vs. So those things will never give the Vs, so there's something missing. And the missing part, that was called also stupidity part, because it's due to our stupidity that we don't know it exactly. This is called the exchange correlation part because of the different effects that are subsumed there that we think about as exchange effects and correlation effects, but this goes into details now. So this is actually a definition for the XC. Okay, so the potential in a non-interacting system is equals to potential in the interacting system plus the Hartree potential plus the unknown XC part. And now we know that we can use this potential, if we have it, to solve in the non-interacting system here and get the same density. But we need to have this thing here. And that is where DFT or Kohn-Sham DFT gets on people, practitioners got extremely creative and clever to derive a huge universe of approximations. So they started with very crude and simple approximations that worked already quite well in certain settings. Then people got super excited about it. They had at one point better computers, they had better approximations. They solved more and more systems, applied this to more and more settings. And in some cases it worked, in others it didn't work. And what we are doing now with people in Hamburg and other places is deriving equivalent approximations for settings that involve polaritons. Okay, so that I explained more or less already. To solve the Kohn-Sham system, just put in the Vs that we have, solve the one particle Schrödinger equation, get orbitals, enumerate them from the bottom to the top, that is in eigenenergies, and put them together. And then the density is just given as the, oh, there's a square missing, as the norm squares or the absolute value squares of the orbitals. So I have this very nice orbital picture that is super useful in chemistry. I mean, chemists were already used before DFT, they were already used to think in orbitals. I think that's why this received so much acceptance also in the chemistry community, because you have these nice orbital pictures. You have this very useful method. And if you even have good approximations, then yeah, you're done. So I should say, of course, this is a self-consistent procedure, just like Hartree-Fock, because in the next step, I mean, this VXC was always density dependent, you know, because it had to be such that the densities match. But the density I don't know, I want to solve for it. So what I do is I make a guess, I put it in here for the Hartree potential, for the XC potential. I solve for the next step, for the next density, I put it in again, and I hope it converges. It will not converge, so I use some convergence tricks, make it converge, and then hope that the thing that is made to be converged gives a useful answer. It will never give the correct answer, because I used an approximation in the first place. The final step now is to extend, okay, this is an established method. This has been around since 60 years, extremely refined, implemented in very many different quantum chemistry packages. Yeah, you can download them, put in a little prompt, and you get out some nice energies and densities. But we want to extend it to polaritonic systems. So now the internal variables change at first. I built on DFT, so the first part stays the same. This is still the one particle density. And the other variable that I add, okay, there are different possibilities, but our standard formulation uses the expectation value of this A operator that you've already seen on the first day and especially on the second day. This is the transverse vector potential as in operator form, and the expectation value for a wave function that includes the photons, of course, gives you the expectation value of the A field, and that is my internal variable. And then what couples to that? Well, I know what couples to the rho, that is the external potential V, the scalar potential, electrostatic potential. What couples to the J is an external current. So I'm thinking about an external current, some coils out there in the universe that act on the photons inside and create some A field here. And those are used as a control parameters because in the end in DFT, I want to find V and J in order to give rho and A that I already put there or that I chose in the interacting and in the non-interacting system. Now, we can also talk about a different level now because we have interacting, non-interacting, but we can also decouple from the photons in principle. And Ita will show you a little bit how we usually construct that. Okay, so the dual pairing, the potential energy, the first part stays the same. This was from the previous Hamiltonian, just the external potential and the density integrated over. And how does it look on for the new variables? Well, it looks exactly the same. It's just that here there's a little dot that is an inner product between three vectors. And how we used to like to write it is just with this dual pairing notation that looks like a scalar product. And that, in total, gives me a system of equations that one can call Maxwell-Pauli-Kohn-Sham system if one does the Kohn-Sham approach for that. And this system can be thought of non-interacting. So first I switch off the interactions between the electrons, and it can be decoupled from the photon field. But I mean, if you decouple from the photon field, the particles cannot interact anymore in QED, right? Because the interaction between the particles is mediated over the photon field. And instead of a V XC, I should also define a J XC if I want to have this full formulation. I mean, usually we do some reduced formulations. And from this point on, yeah, we continue with Ita's second part, which will really use this framework and make it applicable. Questions?
The expectation value of A enters essentially. So in the first line, the expectation value of A enters, and then you essentially do the iterative loop always with the expectation value, right? Can I think about this as like a self-consistent mean field, or is this exact in some manner?
No, it's again like formulated before at this level where I define a universal functional, which I would do in the exact same form. So the universal functional would minimize the internal part of the energy over all wave functions that give you predefined rho and A. So that would be the universal part, exactly in the same way as before. And then at this level, it is still everything is exact. So I can show you. So here in the DFT formulation, oh, where is it? Here. So I have a universal part of the Hamiltonian that is without the coupling, okay? The coupling was those two terms that I showed you. So in QADFT, I have a coupling between V and rho and between J and A. So these I leave outside, but all the other terms I leave inside.
J is external.
Yeah, J is external.
Like a coil.
So J doesn't include internal currents?
No. This J, how I wrote it, no. Ah, sorry, I misunderstood the question. Yeah. Or I made it too complicated. But then I can still say that. So now I would have a universal function just in the same way that depends on the rho and on the A.
Thank you.
So the nice thing about this formulation, it's very straightforward to formulate any functional theory that you like. I mean, of course, there's a lot of subtleties that you have to consider, but the basic structure is always the same. The hard part is to make it mathematically strict, maybe, because there's a few things to look at, like over which spaces is this defined and so on. But if you don't care about that, the hard part is still left to you as finding approximations that are useful. And usually for finding approximations, you always look for reference systems that you somehow understand very well. Like historically, this was the uniform electron gas that you could easily solve, and then you use this as a basis and you build all approximations on top of that. So yeah, it's break time. We're a little bit overdue time, but not so much. So we continue.
5 minutes. What is it? At 50, 10:50?
Yeah. 10:50. Thank you so much.
Okay, so in this second part, at the end, basically you are going to build up your QED functional. And then basically I'm going to let you go through how to build up one. And at the probably in the morning we don't have any chance to run the Python code. So in the afternoon, the first section we are going to focus on the notebook. But in this second part now, I'm just walk you through how to derive those functional. But there are also many quizzes in between, so I will just walk around and ask you guys. So the first thing is that, I mean, like after this lecture, basically you should know how to explain what's the QEDFT, like the mapping Markus just showed. And if you don't know, I will show you the answer. But I mean, like before I show the answer, I need you guys to discuss with each other. Okay, and after that, then basically we are going to use a so-called local force balance equation to construct the exchange correlation functional, because this is the unknown part for solving the QEDFT or like a DFT. And after we introduce the local force balance equation, and basically we are going to use that approach to construct the electron-photon exchange correlation potential. Okay, so after that, then we are going to derive the electron-photon exchange potential, and then we are going to run like there's the whole book, notebook to construct using like a 1D soft hydrogen to construct like the electron-photon exchange functional. Okay, so let me give you just a very quickly like a review. So this is a DFT make easy, and if you are more like a rigorous person, you can complain. Okay. So the first thing is that we start from this matter Hamiltonian. So now we haven't introduced any photon. So as Markus already showed, we start from this Hamiltonian, which has a kinetic energy, electron-electron interaction, and also external potential. So once you have an external potential, basically you can solve in principle, if you solve the Hamiltonian, you get an exact wave function, right? And once you have this exact wave function, basically you can compute any physical observable. But the issue here is that if you use this approach to compute the wave function directly, then you are going to hit the exponential wall, because once you have more electrons, then it becomes more cumbersome. So that's why we introduced the density functional theory. So the idea is like once you have an external potential, basically it will give you the exact wave function, and from the exact wave function, as we already talked about, like once you have a wave function, you can compute the exact expectation value of any physical observable. So here, this is the electron density. And there is a theorem called Hohenberg-Kohn theorem. Basically, there's if you know the density, you know the external potential. And if you know the external potential, basically you know the electron density. So there's a one-to-one mapping. And it means if you start from this a square sine and a square, then basically you notice that this wave function, exact wave function, implicitly depends on the electron density itself. So the physical observable you are looking at basically depends on the electron density. And it means this quantity becomes functional because you need the functional means is a function of a function. Okay. Yeah. So one example is like if we have energy, then basically this is a so-called energy functional. Okay. So now this is a basic idea of a DFT. And in order to compute this electron density, because once you know how the energy functional looks like, how it depends on the electron density, then you solve the problem. But the real issue here is that you don't know what is this, how to compute this electron density. And also we don't know what is the exact form for this energy functional. So in order to find this electron density, basically we are going to use another auxiliary system, which is a non-interacting system. And this non-interacting system we choose as a constant system. So the constant system is like, here this is a short review. So if you have an external potential, you get an exact wave function. From the exact wave function, you get an electron density. And from the Hamburg-Combe theory, basically there's a one-to-one mapping between electron density and the external potential. Okay, and we can also do the same thing for non-interacting system. So when I say non-interacting system, it means electron don't interact with the other electrons. So we don't have like a electron-electron interaction in this picture. So here what we have is like another external potential. But this external potential we call it Vs, and this Vs it will contains the I'm going to show you here. So you can see like this is a constant Hamiltonian. So constant Hamiltonian is composed of like a effective single body Hamiltonian. And this single body Hamiltonian, you can see like there's a kinetic energy operator, and also this Vs. And this is a kind of like another external potential. And this another potential, how is this external potential related to the original external potential? So the relation is like this Vs is equal to the original external potential plus the Hartree potential. So the Hartree potential can be obtained from classical electron dynamics. Once you have an electron density, then basically it's included here. But because the electron is a quantum particle, so in order to capture its quantum effect, basically we introduce a so-called exchange correlation potential. And why is called exchange? Because if you exchange the position of two electrons, basically you are going to get a minus sign. And there's the corresponding potential is called exchange. And the other thing we cannot capture by this exchange is called correlation. Okay, so this is a so-called exchange correlation potential. Okay, so once you can solve this single body Hamiltonian, basically you are going to get the wave function. Okay, so this is at the bottom line is very easy to solve because it's a one body problem. And if you get the wave function and you take the expectation value and the square term, the modular square, then you are going to get an electron density. And if you know the electron density and the energy functional, then basically you solve all the problem. Okay, but here the unknown is that we don't know what is this exchange correlation potential. We also don't know what is this energy functional. So that's why I mean like the whole business of a practical DFT is try to find some approximation for this exchange correlation energy functional. And the relation between them basically is like the functional derivative. Okay, so here I already introduced what is DFT and what is the constant equation. and how to solve the quotient equation. So the question for you is that now you guys need to discuss with each other, and then I will ask you. And then, so you have to introduce what is the DFT mapping, and then how to get the corresponding quotient potential. So I will give you 5 minutes. And if you have any question, just raise your hand. I will say.
Density and
Slide, please.
Okay, which one? Previous one.
Thank you.
So that's different.
Yeah.
You're only concerned about the number. Oh, okay. This point. Yes. Largest number. It is smaller or equal to all elements of the the minimum needs to be part of that. The minimum doesn't need to be part of
Like you said, the minimum is not necessarily
Let's call that set A.
Oh yeah, that's suppose. No, that one is exact. Yes, it's very hard to solve because
the lowest bound is the highest bound is same as the lowest bound.
I'm like
There is no
you can solve the function like
and go always
this is single
closer to the boundary. You're never exactly there. And that's why you stay outside. Eventually, here you don't go.
Yeah.
Yeah, exactly. Define it in direct way. Very good.
Yeah, that's right.
That's why in math you usually always try so because you know this. That is especially true for sequences.
I know that there is always close points where we can numerically
of course, numerically, I cannot change compare those. Discrete space. It appears all the time in our theories. Because usually we'll say, I have a whatever calculation is self-consistent, so it gives you every step it gives you away.
For the electron, we still
energy always closer to the sun. It never reaches.
There's an electron.
Numerically, I don't think about it.
Yeah,
that's the trick.
But any sequence will usually have any increasing sequence will have an infinite, but rarely has a minimum. Yeah, because a minimum would mean at one point.
I think if you use a tensor paradigm, say like electron fermion, and you combine.
Usually, we'll always get a little bit better than the next step because you don't care anymore. Even numerically, you don't stop your iteration until very active. Stop it. I don't think you usually merge
No.
You can always get more out. Yes. No, it's not in.
Yeah, that's correct. Because we assume it's a non-interacting system. So non-interacting for the non-interacting system, we can use a Slater determinant.
The extra path.
Yes.
And it's interesting. Those are quantum mechanics like
Yes, later determinant. Yeah, because once you know, like once you have a later determinant, it's very easy to compute the electron density. Yeah, because they just take each orbital square and then sum of them. Yeah. I mean, like if you choose another system, which is not
yeah, but it can still be a ground state.
Right, but no problem. Density. So what's this ground state? It's a different
So that will be that the problem is
yes, yes.
one energy and many potential. And let's assume there's no efficiency. Then you could say actually the same holds for the.
Because for the initial system, we don't know how to find the electron density, right? And then now we need to find the electron density, the red one.
That's the idea.
And then we have to map to another non-intelligent system, which is like a stator determinant. And for the stator determinant, it's like you solve the single particle wave function, like the bottom one is a single particle Hamiltonian. And for the lowest wave function, you can directly compute the electron density. Yeah, that's right. Yes.
It just depends on the continuity.
No. Solve one. Yes. Yeah, but the problem is like you don't know what is the exchange correlation potential.
It's a lot to what we do.
Yeah, so that's why I mean, like we have to find some approximation to the exchange correlation energy and also exchange correlation potential. If you have any question later,
I mean, yeah.
In slides or I'll post it later.
Okay, I would say I think you should also look at conversion.
Okay, so let's come back. And then now I'm going to show you the results. I won't bother you guys too much. Okay, so I'm going to show you. So the question is that how do we apply this DFT to the line matter couple system? Okay, so here you can see like we start from many body polyphase Hamiltonian, and in this case is in the wavelength long wavelength approximation. So the question I want to ask you, what should I put in the green box? If I couple the matter system, here is the electron I couple to a photon, and then what is the two green box I should put? Yeah, you want to try? Oh, you want to try? Good.
So the first box would be like adding the vector potential, squaring it.
Yes.
And then the second box would be the vector potential applied to with the kinetic operator of the nuclei. So the nuclei plus the vector potential squared. Okay,
good. Very good try. I mean, like the first part is right. Yes, and the second part is like compared to the DFT, we have an external potential coupled to the electronic system, right? And what's something we should couple to the photon field? To the what? To the current. Yes, to the current. Okay, you guys are here. Yes, that's right. So good. So you can see like this one, you have a internal vector potential is A, and we also have the external current coupled to the photon field. Okay, so now you can see like from the DFT setting, we have an external potential coupled to the electron density. And now if I couple to a photon field, then what is this two green box I should put? I just answered the question.
Just a question.
Okay, good.
So we have quantized essentially all of our electromagnetic environment.
Yes.
So, and J is not the current in the material.
No.
What is J in this case?
In this case, it's like you can think about it's like a cavity. You pump the cavity.
But I pump it with essentially an electrical field that I don't include explicitly in my Hamiltonian, right?
Mm-hmm.
So I don't. Is this the same as if I would include all the electromagnetic field and then I put my EM field into a coherent state? So can I think about it like this? Because I've seen this approach a few times, that you have a quantized A field,
mm-hmm.
and you say you have an additional classical A field or current in your theory.
Yes.
And I don't quite understand how this comes about from like an ab initio Hamiltonian.
I try to understand.
You also have a classical E external here.
But this comes from the nuclei, right?
Not only. I mean, I use it in a Concham approach. I use it. I think about it as a control parameter, because in DFT you also have this auxiliary system where you need to choose the external V such that it gives you a certain density. You're right. In the physical system, you have a physical understanding where this comes from. And it could come from the nuclei, but it could also come from some external trap, right? Could come from some experimental apparatus, whatever, or it can just be modeled. So I think there's many applications where this, you just give it, you apply a harmonic potential from the outset, something like that.
Mm-hmm.
Then you wouldn't say it comes from the nuclei. So,
okay.
Yeah, there can be many reasons, but then also always in DFT, you also have this idea of an auxiliary system that does not need to be explained physically. It's just there as a computational tool. And there you don't care where this comes from. You just put it into the Hamiltonian as a parameter.
Okay.
And this is the Vx and the Jx.
Great, thanks.
And also, if you think about it, when you create a coherent state, you still take some instrument and also get some charges. And that's what creates excitation of the photon field, right? So it is charges at the end that you move to create pulses. Yeah. And it's charges that you move to detect pulses. So it's always some external classical thing that you're doing to the system to observe it and probe it. Yeah. So conceptually, that's the sort of way that you should understand it.
Okay, so
no matter what you do to a quantum system, you're doing it classically somehow.
The choice, the natural choice for the physical system here would be exactly as you said, Vx nuclei coming from the nuclei, Jx equals 0. Just you need it later to formulate the Concham system. That's why we put it already now.
So I mean, like to answer a quick answer, it's like we can also have a different choice for this starting point, and yeah, I mean, like here I just chose one more like easier for me to understand.
Thank you.
Okay, so
can I ask, so it's very navigation. Don't we need to put the spin term?
Yeah, you can also do that.
It's already.
But because here I do like a long wavelength approximation, so that's why I mean like the spin will couple to the magnetic field, so you have a Zeeman splitting. Yeah, you can in principle you can do that. But here I do like a spinless system.
Yes. I just
yeah just.
So in that case, so in the electron case, it's kind of easy to guess. We need to put just a Zeeman coupling, but what about the current?
Yeah, because here you can see like
I just want to know what kind of time, what kind of time we need to put.
In order to do the DFT mapping, as you can see, like we have to do like external potential. It will corresponding to the electron density. Okay, and for the photon field we are discussing about is like this is an internal quantity A. So in order to do the mapping, we also need an external one. Yeah, and the external one is basically in this case is an external current. It will couple. It's a classical external current, and it will couple to the photon field. Okay. Yeah. Okay. So now the question is like these two grand box. How many of you already know the answer? Raise your hand. And I will ask those no. Don't raise your hands. So who knows the answer? Okay. Just two. Okay. Do you have any guess? Maybe I can just walk around. Do you have any guess?
Current J.
Yeah. And what is the other side? The internal pair.
Quite sure.
Okay. No worries. Yeah. So the answer basically is like we need a external potential, scalar potential, and also like the current, external current. It will couple to the internal pair. Okay. So this is a basic, like a basic QEDFT mapping. And now we are going to use this mapping to do like set up the non-interacting system. So as you already see, like we have an external potential and external current. It will give you the exact wave function. And from this exact wave function, basically we can get the electron density and the photon field. And there's a theorem proved by Lugi and others. There's a one-to-one mapping from this external potential and the current to this internal pair. And similarly to the DFT, we also need to, in order to get this electron density and the vector potential, then we will rely on a non-interacting system to construct these two. So the way we do is like we map to a non-interacting system, and this is a tensor product of the matter and the photon state. And this one, it will corresponding to another mean field external potential and mean field external current, but they are different from the original one.
Are the electrons and photons assumed to not interact in this auxiliary problem?
Yeah, they are not interacting.
So there's no polaritons here? Or that's kind of coarse-grained out?
I think in this case, because the quantity we are looking at is just how to reduce this internal quantity. And if you want to understand what's the other physical observable, it should be another like a kind of like a functional. So it's a functional depends on these two internal quantity. Yeah. I mean, like I will show you later how to, when we run time dynamics calculation, basically we can see kind of like a polarization shows up. Okay.
I mean, in principle, here you have not removed any photonic degrees of freedom.
No, not yet.
So you could, in principle, still see polarity.
I mean, the next box shows it, I think.
Oh, so everything is still in there. It's just when you throw one out that you might not see the polarity, which I guess you will show later.
Mm-hmm. Yes. Okay, so now what I'm going to do is like we have to find the non-interacting system. And the non-interacting system here, we focus on the static case. So as you already see before, this is the first one. This Hamiltonian is for the matter system. And in this Hamiltonian for the matter system, you can see we also have an external potential, and plus a so-called mean field exchange correlation potential. And mean field, if you neglect, like for now, let's say if there's no photon, basically this mean field exchange will become back, it will go back to Hartree exchange correlation potential. Okay, but in this case, once we have a photon inside, then we are also have some contribution from the electron-photon interaction. Okay, and in addition to this one, we have a mean field from the photon system. And in order to solve this A vector potential, basically another non-interacting system for the photon system is we solve this Maxwell equation, because now we are looking to the time independent case, so there's no time dependent here. And in order to solve this vector potential, basically you can see we have an external current, and we also have the current from the matter system. It generates a current, and in order to capture the some like a quantum effect, we put another so-called exchange correlation current. Okay, and this one is unknown, and also this one is unknown. Okay, and the approach we are going to use is so-called local force balance equation is to find this one. Okay. Yeah.
Maybe you mentioned it, but is the J is
that like the
transverse one?
Yeah, is that like the Hartree term in the matter case, or
the J?
Yeah.
This one.
Right.
This one is like if you run time-dependent calculation, basically you have a wave function here, right? And this is a matter system, and the matter can also generate the current.
But that would
okay.
Coming from the Contram wave function.
Yeah, but it's not analogous to the Hartree term in the. It's not like something we put in because we know it easily, and then we put the rest in the exchange correlation.
Yeah, you're right. So yeah, this one is kind of like a Hartree. Yes, I okay. So yeah. So now I'm yes.
So I want to understand. So how does the phi naught look like? Like, is it like the electron part is the Slater determinant of n electrons that has been specified, right?
Yeah.
But what does the photon part look like in phi naught?
So I mean, like here, basically, we don't write this photon state directly.
So it's just a classical field.
Yeah, so. Classical field, like a field.
Okay.
Yes. So now I'm going to.
Right. So you have a time-independent problem, but you have a current in there.
Yeah.
In equilibrium.
This is a paramagnetic. Sorry, this is a paramagnetic current.
Can I have a current in equilibrium?
I mean, like the physical current is 0, but you have the paramagnetic and the diamagnetic current.
Ah.
Okay, so now I'm just
maybe just to add.
Yeah.
But the thing is that there is just like symbolical, right? But you could have like finite current, but also fluctuations of the current. As least the way I see it, it's still function like if it was an operator somehow, right? And it can still have fluctuations. So it's not really the expectation that you still have to minimize and solve separate.
Oh yeah.
The fluctuations can kick in. You don't really have to have physically a current inside the system.
Okay.
Yes. Because I mean, you will show probably that what you map then is the fluctuations of the operator.
Okay. So now I'm just walk you through the whole history of the QEDFT functional development. So basically, this kind of like setting is actually starting from 2011, and basically also like from Angel's. This is actually Ruki's paper. So he started from like develop a so-called time-dependent constant equation for the QEDFT, and after that, at 2013 and 2014, basically there's 2 papers construct like a foundation of the QEDFT. And if you are interested, you can look into this paper. Basically, they set up like from the time-dependent case, and also can apply to the steady case. And in 2017, then basically there are some like ground state QEDFT mapping. And so basically, you will map. Initially, it's like a external current, but you can kind of like map into the electron density. But if you are interested, you can look into this paper. And after that, so this is a kind of like a ground state setup. And in 2019, there's a linear response theory for the non-interactive, non-relativistic linear response in QEDFT. And this one, I think Johannes will talk about this tomorrow. And in 2020, basically, for the QEDFT, usually what we look at is like an electron and a photon. This kind of like a couple system. In 2020, they applied like a generalized this approach to like an electron, nuclear, and photon system. And in 2025, and also in from Angel's previous group, basically we have like a relativistic linear response in QEDFT. Okay, so this is on top. Basically, it's like a general theory development. And now I'm going to go walk you through the functional itself. So you already know, like in the polyfield Hamiltonian, we can return in terms of like in the length gauge and also velocity gauge. And people start on the length gauge. The first electron-photon exchange functional is developed in 2015. And also like they can reverse the process to find the exact exchange correlation electron-photon exchange correlation functional using so-called fixed point scheme. And in 2017, this is the first work about like using QEDFT to show the spontaneous emission. In 2018, this is the first 3D AB initial calculation for real molecules. And since then, there are also different works like initially like in 2018, before basically they use a so-called like they use a wave function to construct this potential exchange correlation potential. In 2022, they kind of like push into the just compute the potential using the electron density. And there's also go beyond. In 2023, they start to go beyond the weak perturbation potential. They start to consider the random phase approximation. So basically, start to like can go to like a strong coupling region. And in 2025, this paper basically include like the van der Waals correction. Okay, so now in the rest lecture, basically I'm going to focus on the velocity gauge. And the way we are going to construct the functional basically is based on the local force balance equation. And this local force balance equation, you will avoid some mathematical issue like a functional derivative issue. Okay. And this approach basically is started in 2021 in this paper. And since then, we kind of like extend this approach to more high dimensional material. And also like in 2024, we apply this one to the real solid state material. It's like an extended system. Okay, so now I'm going to walk you through how to construct the electron photon exchange functional using the local balance equation.
So in the previous slide, so in which condition or materials do we need a relativistic linear response?
Heavier atoms, like because
in orbital coupling.
Yeah, that's right. Okay, so now you already know how to use QEDFT, and probably you discuss with each other how to do this mapping. And so the next step we are going to go another jungle is to construct the exchange correlation potential using local force balance equation. Okay, so what is local balance equation? So I introduced this approach using like a just a matter Hamiltonian. So here we have a kinetic energy is electron-electron Coulomb interaction and also external potential. And using this one, so this is a question for you, and I will give you maybe 5 minutes if your math is good to solve this problem. Okay, so I mean like we are going to derive this formula. Start from this paramagnetic current operator, and then if you like derive the equation of motion for this one, And can you reproduce this formula? This is a question. Yeah, so now I have let's start like 5 minutes.
Start from below.
So this is a hint, like you start from the Heisenberg picture and derive this formula.
Sorry, we lost it 30 seconds.
Yeah. So take the
The importance of the local force balance. Like, what would happen if we don't use it?
You don't. I mean, like in the approach we use is because we want to construct the exchange correlation potential directly, without rely on the energy functional.
Okay.
Because for the standard DFT, you need an energy functional, right? And you need to do the functional derivative to get the potential. But in this case, we get the exchange correlation potential directly without rely on energy functional.
Right.
Yeah. So you are going to see how we are going to construct.
All right.
FT. Great. Was it commute? You mean? No, because the definition. I mean, it would commute with the gradient, absolutely, but not with the delta question. If you want to write.
So you don't have to write down the blue and the orange one. You just focusing on how to get it done. Because for this one, it's the answer is already here.
This one is the
But where's 0? I mean,
which you can do. We change now in our next book.
Because it's like then you go to row
because the reason is that
you could swap.
Yeah, you could swap. You can always through Maxwell's equation ever want.
Yeah. So why was it done this way?
V is given already. You
Yeah,
can change that.
but then you could have used AX and J.
And it doesn't look like QED. You don't see the QED then.
It's still there. That's
sure. You can always go from one. But for QED, the A is much more natural.
And now you're changing to
rho to potential.
In the internal what?
Potential. Let's say call it phi.
Yeah.
And then a vector. So
expectation.
That's internal.
Okay.
Rho means that the gradient applies like to the left. Okay. Only to the left.
Because then you can write this. And this is not only something about the mu, it's also the base integration already. And then you see the full dual structure. Just by writing these things up.
That's pretty cool.
That's exactly
The blue don't change.
Okay.
I guess.
Yeah, because I mean it's a little bit disturbing that
absolutely.
It's mixed.
It's a theory in development.
know what you want to get out. That's why they're asking you.
Take a neutral letter.
Look at this. The commutator of J and
yeah.
Otherwise J would depend on time.
Yes.
For the red part, I mean, you just bring up the wave function and you
No, they don't exist anymore. They're just part of the geometry of the spaces.
Condense them in a tensor.
Yeah, that so going down into the index is like solving mechanisms. Just like
can you now write it as an operator that has two indices?
Yeah, absolutely.
I think that's also what you showed last time.
Yeah.
no, it's not true.
Yes, you're prepared. Yeah. No, I just see it like you're faking. Yeah, it's
obvious
connection.
Oh, but it's like
Do you need, is anyone need more time? Does anyone need more time? Raise your hand. Like to derive this formula.
We said the derivative equals
Okay.
Need to be conserved. I mean, they'll think so. Need to be conserved.
Yeah, because then like, so basically, I think what we
This
need
is
to
just
show
a matter
is that the
without
commutator
photon.
of J
We haven't included
is
photon yet.
external is equal to rho times
Current.
external. Because that in this, because in the static case, force balance, the time derivative equals the commutator of zero.
Does dj dt need to be zero?
Oh yeah, in this case, we take like a static case. Static. Yeah. Yeah, that's right.
In the red thing. Now, why is there no arrow?
Oh, we're going from that to that.
So once you get like the equation of motion for the paramagnetic current, you have to, we are looking into the static case. Okay, so you have to make sure the time dependent vanish. Then you are going to get the formula.
You should come here more often.
Why is that? What is the error again?
Where does it?
Yeah, that's good.
This is the equation. So.
With a good head.
Okay, then I will show you the derivation very quickly. What happened? Yeah, okay. Yeah, so basically we start from this J. Okay. And then once we have this one, then basically we are going to get the equation of motion for this paramagnetic current. And what we are using is like this Hamiltonian. So you take the Hamiltonian here. And basically what we do usually is like when you try to solve any problem, don't beat the big boss. You have to split. Okay, so that's why I mean like this Hamiltonian we separate into the kinetic energy and electron-electron interaction, and also the external potential. And as I said, like for this guy, we define we define this one as ft, and this one, oh shit, sorry. This one we define as fw, so we don't have to solve this one. And the question I ask is like the one we should focus is this guy. So you can see this is the external potential, and we have a ferromagnetic current, and it involves some operator, this operator. And again, we separate these two terms below. And once you separate these two terms, then basically we just solve each one. And for this, the first term basically is this commutator. And in order to compute this commutator, basically we take the second part, operate on the first part, and there's a minus sign. Okay, so you get this one. And the other term is very similar. So at the end, basically you take the expectation value for the exact wave function, and the density is you can compute the density using this guy, and then at the end you get this one. Okay, so this is the local force balance equation you get. Okay, good. And the reason I walk you through to this equation of motion because it's like the tool we use to construct the exchange correlation potential. So now you already know how to derive the local balance equation. Okay, so now we are going to use the local force balance equation to construct electron exchange correlation potential. Okay, so now let's see. So this is a Hamiltonian you just see. We haven't dealt with photon yet. Okay, and this is a local force balance equation for the static case you just saw. And now I also have the constant system, which is a non-interacting system. And what is the corresponding local force balance equation? And I will walk around to pick up this question. What I should put in the green box? You guys have any answer? You want to try? Does anyone want to try to guess?
Right, there would be no FW.
Yeah. Okay, good. And what is the subscript? Like you notice that like there's an exact wave function.
Phi.
Yes, fine. Okay, good. So now we have two local force balance equation. One is like this is a exact like a external potential, and this one is the mean field potential enter into the constant Hamiltonian. Okay, and this will rely on the here. This is a selected determinant. So now if I subtract these two guys, then we can define so-called mean field exchange correlation potential. Okay, and this one it will depend if you know the exact wave function, and then you can solve the potential. For example, now if I choose let's say I choose this is an electron interaction, and if I replace this exact wave function with the selected determinant, then I define the corresponding potential is a Hartree exchange. Yeah, so if you know this one, you can write down this explicitly using the constant orbital. And once you solve this Hamiltonian, this Poisson's equation, then basically you are going to get the Hartree exchange potential. Okay, so this is a way how we using the local force balance equation to construct the electron exchange potential. And you can also do a similar thing for the correlation potential. Okay, and here you can see like we don't rely on energy functional, so we can work around avoid the functional derivative. Okay, so now the next thing is that we are going to include this.
Thank you. So you divide them by the density, and this might be small at the tail regions. Is this approach numerically stable? Like, you actually make it converge?
Nicholas, no, Nicholas is another our group member, and he know how to do this numerically. Yeah, yeah. I mean, like in principle, if you don't know which like a numerical method, then you will become a problem.
Okay, so it's as nasty as it looks.
Yeah, I mean, like especially for a molecular system, but for the solid, if your electron density is everywhere, it doesn't manage, then it's fine.
Okay, thank you.
Yeah. Okay, so now we are going to include the photon field, and from there, I think you have some idea about how to construct the exchange electron-photon exchange correlation potential. Okay, so this is our starting point. This is a polyfield Hamiltonian within long wavelength approximation. So what we do is like we couple to the photon field using minimum coupling, and then as you already done in your exercise here, if we can expand this two term, this term, so you will become one is a linear and the other one is a square term. And for the square term is called diamagnetic contribution. So we can absorb the square term into this photon operator. Okay, so you will become the so-called dressed photon. I think you already done this in your exercise. Okay, so this is a starting point for us to find the function like electron-photon exchange potential. Okay, so we start from this polyfield Hamiltonian in dressed photon representation. And so basically, we also want to get the local force balance equation, like this one. So this one is from the kinetic energy. This one is from the electron-electron interaction. And now we have an additional term. And this one is from the ferromagnetic current. And then the next thing is that we also have the constant system. And the constant system we choose is like we have a vector potential here. And this is a mean field, like a scalar potential. And similarly, we can write down the local force balance equation for this guy. And you can see like because electron, in this case, they don't talk to each other, so we don't have the corresponding electron term, but we have the one term from the electron-photon interaction. So we take these two local force balance equation and we subtract them to define the mean field exchange correlation potential, as you already saw in the standard DFT one. Okay. And then now this is a trick we do because this vector potential in the steady case is a constant. So we can rotate the constant orbital to get rid of the constant vector potential. Okay, so this is our starting point to define the exchange electron-photon exchange potential. Okay, so now you already see how to use the local force balance equation to construct the exchange correlation potential. So now we are going to using the approach to define the electron-photon interaction. Okay, so the way we define the electron-photon exchange correlation potential is like from this term. We take this term out, divided by the electron density, and we define the corresponding potential is electron-photon exchange correlation functional. potential. Okay, and the next thing is like some approximation, because for this exact wave function, it contains the electron and the photon. And now what we are doing is that we are going to replace this photon field in terms of the static determinants for the electronic wave function. And then another thing is that you can see like once we replace this exact wave function to the just a matter static determinants, we still have the photon operator here. Okay, but this photon operator doesn't operate on the electronic static determinant. So we have to do some approximation to capture the effects from this photon operator, especially the quantum fluctuation. So what we do is like we replace this photon like a fluctuation, like a quantum fluctuation, in terms of the matter current, ferromagnetic current. And this approximation is called we call it like a bright type of ansatz. And if you are interested, you can look into this paper to see how it behaves. And one thing I want to mention is that this approximation only works well in the following condition. One is like it should be high, like your 9-meter coupling. So lambda here, that is corresponding to the 9-meter interaction strength. So if your 9-meter coupling is quite large, then basically this approximation works well. And also high failure frequency, it will also works well. And also like if you have many electrons inside the whole system, then it will also works well. And there's another approach from Simone and other people. They start from the polyfield Hamiltonian and they do like a high frequency extension, and they can kind of like also get this kind of like expression. Okay. And in order, so this is approximation we have done here is like we choose for the electron photon exchange. And in order to go beyond exchange potential, then you can look into this another paper, which is from Lucas. Is also in the audience. He used Monte Carlo like a QMC method to find this correlation energy. Okay, so now it's your turn. So now I give you 5 minutes to explain to each other about how to use this local force balance equation to construct the exchange correlation potential. Yeah, you can just describe how the process work with each other, and I will give you probably 3 minutes.
Yeah. So we want to auxiliary Hawley coach all that parts of like
So the question is that how to explain to each other how to use the local force balance equation to construct the exchange correlation potential. Yeah.
Having the photon operators act on the electronic waves. It seems that I wasn't sure about the end result is you can exchange
When they have the delta symbol there, or is that like the change in the fluctuation of photons? Yeah.
Well, my idea is
the current, which is actually have so strong coupling that A equals
Okay, so let me give you if someone asks me about how to use the local force balance equation to construct the functional, basically I will go like I will explain like this. So I mean like we start from the 4 Hamiltonian, and from the whole Hamiltonian we construct the local force balance equation, and similarly for the non-interacting system, we can also write the same like another local force balance equation, and basically we subtract both of them, and then we can define what the so-called mean field exchange correlation potential, and from there we separate each term to define what is the exchange and what is correlation. Okay, so this is a way how we using local force balance equation to construct the corresponding potential. Okay, good. So now I think
explain intuitively why the difference between cone charm and real external potential is the exchange correlation potential. So why is this difference my exchange correlation potential that appears in DFT?
What is the question again?
Why is what we've done now, so the difference of external and cone charm, the exchange correlation potential? Because I thought the cone charm potential is essentially an auxiliary quantity that doesn't really have physical meaning. But now we're giving it the meaning of like the exchange energy, right?
I see. So because the mean field scalar potential we are giving now, it should be like connect to the original external potential. And what we do is like, for example, for the Hartree potential, basically you can see is from the classical picture, like if you have a density, then basically you can construct a Hartree potential. But because their electron is a quantum particle, so there's a quantum effect inside. And you can see like why is equal exchange correlation, because if you kind of like separate, you just take the zeta determinant, and you will obey the exchange principle. So if you do this, you take the zeta determinant and then put it into like the Coulomb-Quinn interaction. Basically, you are going to see this. You will include the exchange potential inside, and the rest about like a quantum effect. For example, if the electron they are very close to each other, they will feel each other, and the rest we don't capture that is a so-called correlation. Yeah.
And that is contained in the difference?
Yeah, yes.
Actually, the definition. You can take two definitions.
The Quantum potential is the sum of the external and the exchange correlation.
Ah, okay. Ah. So by definition, this
by
is
definition.
Okay.
I mean by construction.
Okay. Thank you.
Okay.
In the last slide, was the capital psi the electron photon exact wave function?
This one?
Yeah.
So this one is an exact wave function. Basically, it contains the electron and the photon. But here, what we do is like we replace this wave function in terms of like just a matter-slater determinant. Okay. So this is one approximation we did here. And another thing is like once you replace this one, it becomes just a matter wave function. But you can see here you have a photon operator.
That was That's why
and if you naively operate, then you will become you will come. But so in order to capture this quantum fluctuation from the photon field, that's why we use this bright type enzyme. So you will replace this photon fluctuation operator in terms of a matter operator. So basically, this guy will operate on the matter side.
maybe if I might.
Yeah.
So this relation becomes exact. This relation becomes exact also in the case of a homogeneous electron gas coupled to the cavity that we also calculated in the exercises. So if you calculate the forces from the coupled electron photon wave functions, you will find exactly this.
Okay, so here I will just go through, but I mean, like in the afternoon, the first section is that I will ask you to derive this form in a notebook. So basically here, if you know like this F basically is written here, it contains the paramagnetic current operator and the paramagnetic density operator. One is density and the other one is not. Okay. So you take the constant orbital, like a zeta determinant, and then you can compute this one. Okay, and if you do this, then basically you will involve the constant orbital. And but here we can also do like a so-called local density approximation. So basically everything will, this one, it will just depends on the electron density. And then you plug in, then basically you are going to get so-called electron photon exchange LDA functional. And so I leave the derivation in the lecture notes you can look into. Yeah. Okay, so now I just go through the example. So here what we do is like we take the 1D harmonic oscillator. We compute the electron density outside the cavity. And if we put a 1D harmonic oscillator inside a cavity, we can get another potential. So the potential show here, this is a potential difference between inside and outside the cavity. And the black one is the exact result. So we exact diagonalize the Hamiltonian. And then inside the cavity, you can see the electron will localize around the oscillator energy potential minimum. Okay, and if we use a px potential, then you will overestimate. And in order to reduce that, basically we have to consider the correlation effects. Anyway, I mean like the detail you can look into the paper, and we can also use a PSLDA local density approximation, shown in orange curve. And this is in the weak coupling region and the low frequency region. And the PSLDA becomes better if you go to higher frequency region, as I showed before. Okay, and also like a large coupling region, and will also capture the exact result. More close, yes. Okay, so this is another example. In addition to 1D, we can also do 2D quantum ring. So there's a ring, and there's a one electron inside, and we solve the electron density exactly, and show here this is the electron density difference inside and outside the cavity. So along the polarization direction, the electron will localize along the polarization direction. And using the PSLDA, you can see like you can also capture this feature and quantitatively quite well. Okay, so this is the ground state density. And using this method, we can also compute kind of like a polariton spectrum. So what we do is like we include a time-dependent calculation. And this photon field, now it will depend on, this photon field basically follows the classical Maxwell equation. So you have this kind of like a form, and I propagate this wave function and compute the current here. And this current will enter into this vector potential. This vector potential will enter here. So there's a time propagation and interaction between photon and the electronic system. So once we do this, and this is a hydrogen atom inside the cavity, and show here this is a absorption spectrum. If outside the cavity, you are going to see the first peak, and this peak is corresponding to 1s transition to 2p 2p orbital. And if I couple this peak to the photon field and along the x direction, basically you are going to see the rapid splitting will happen. And I also use a James Q-means model, which is quite on top of each other. Okay. Okay, so now we almost done. So we already go through, like in this morning, we already know how to partition the whole system into a subsystem. And then you also know how to use a QEDFT to map the interacting system to the non-interacting system to make the problem easier, hopefully easier. And then the main question in a QEDFT or DFT basically is to find the exchange correlation potential. And we introduce a method called local force balance equation for you to figure out, to find out. And I also show you how to include the photon field. And then we can get the electron photon exchange potential. And in the afternoon, we are going to construct the functional in a notebook. Okay, probably that's all. Thank you. Any question? I forgot.
I mean, I'm trying to understand the physical intuition behind the force balance equation.
Very much here.
But the physical intuition behind the force balance equation.
And because it's force.
Yeah, but it's that there are some oscillations going on in the gravity. Then the matter is kind of like if I just look at the electron watching back and forth between multiple locations.
But I mean, like if you run time-dependent calculation, actually you are going to see that. But here, this is a static case, the ground state. So the ground state doesn't do this oscillation. Yeah. Okay, but if you have any question, I will always here. So, I mean, like always until tomorrow. Okay.